Recently, we've been messing around with some ideas like average value and net change. And I want to take those ideas and apply them to the concepts of distance and velocity. So let's take a look at a problem that we're used to, a particle problem. The particle moves along the x-axis so that its velocity for the first 10 seconds is given by the following function. The particle begins at x equals 5. Find the particle's position function. To find the position function, we'll call it x of t. We're going to use the integral and just take the integral of the velocity, at 3t squared plus 4t dt. And when we take the indefinite integral there, we'll end up with t cubed plus 2t squared plus some constant c. This is our general solution. To find out what that c is going to be, we're going to use this piece of information that the particle begins at x equals 5. So if it's beginning, that's time 0. And so 0 cubed plus 2 times 0 squared plus c. And that position is going to be at 5. So c equals 5, which means x of t is going to be t cubed plus 2t squared plus 5. So how far from where it started is the particle at the end of these 10 seconds? Well, we do have this position function now, that x of t is t cubed plus 2t squared plus 5. So we can just figure out where it is after 10 seconds. What is its position? And that would be 1,000 plus 200 plus 5, or 1,205. And we know that it started at 5. So how far from where it started did it finish up? Well, that would be the end minus the beginning. 1205 minus the 5 is 1,200 units away from where it started. Now, I want you to notice something about that 1,200. Like we said, that 1,200 was the difference from where it ended and where it began. Right? So x of t being evaluated from 0 to 10. X of t was the integral of velocity. That means that distance is a definite integral of velocity. That's super helpful for us, and it should kind of make sense. The distance is the integral of velocity, right, over a given time interval. The distance is a net change. It's a net change in position. And remember, with net change problems, we have to take the integral over an interval of a rate of change. Right? And that's what velocity is a rate of change. It's a speed. Velocity is a rate of change in position over time. So here we have another velocity function, e to the t minus 3 square root of t miles per hour for the interval from 4 to 9 hours. So how much distance gets covered in these hours from the 4th hour to the 9th hour? Remember that distance, of course, is the integral of velocity. So we're going to use our velocity function. And our interval goes from 4 to 9. So we would have to take the integral of that, which would be e to the t minus 3. Let's see, t gets raised from 1/2 power to the 3/2 power. So we have to divide by 3/2 or multiply by 2/3. So that would be e to the t minus 2t to the 3/2 evaluated from 4 to 9. Now when we plug in 9, we'll get e to the 9th. And 2 times 9 to the 3/2 is 54. We'll subtract off, plugging in 4, e to the 4th minus 2 times 4 to the 3/2 would be 16. I believe. So we simplify this, we'll get e to the 9th minus e to the 4th minus 38, which is about 8,010.485 miles, just miles, right? Distance, just in miles. Now, if we want to find the average velocity, remember that velocity is just distance over time. So we know the distance that got covered during these 5 hours was 8,010 miles. And we know that the time interval goes from the 4th hour to the 9th hour, so that is 5 hours. And when we divide those two, we get 1,602.097 miles per hour.